Hi guys, welcome to another video where we're going to look at another interesting mathematics problem, look at the problem solving process, how it looks when approaching a fairly non-routine problem in mathematics. So the problem that I've chosen for this video is from the book Challenging Problems in Algebra by Alfred Posamentier and Charles Salkind. And the problem is from chapter 16, problem number 13. So let's have a look. By the way, guys, this is a fairly new YouTube channel. I've only got a few subscribers at the minute, so I'm really looking to grow the audience for this channel. So I'd be really grateful if you could subscribe to this channel, tell other people about it, and give this video a like, give it a big thumbs up. I'd be really grateful. That'd be great. So, problem number 13 from chapter 16. So the problem is as follows. Show that if the lengths of the sides of a triangle are represented by A, B, and C, a necessary and sufficient condition for the triangle to be equilateral is the equality A squared plus B squared plus C squared equals AB plus BC plus CA. In other words, we've got a triangle, the sides of length A, B, and C, then this triangle is equilateral if and only if, so it's a necessary and sufficient condition that A squared plus B squared plus C squared is equal to is equal to AB plus BC plus CA. Okay. And just for clarification, the problem goes on to say, that is, if the triangle is equilateral, then this equality holds, and if this equality holds, then the triangle is equilateral. So just confirming, just verifying that there are effectively two parts to the solution to this problem. So we can either prove the two parts separately or at the same time. So if we were to use logical symbolism, by the way, so symbolic logic or something like that, I'm going to use fairly informal symbolic notation. We might say that this is statement A and this is statement B, for example. So symbolically, what we need to do is we need to prove this implication, A implies B. In other words, if this triangle is equilateral, then this equality holds. But we also need to prove the converse implication. So B implies A. In other words, if this equality holds, then the triangle is equilateral. It might be tempting, particularly when you're kind of starting out with logic, getting used to the ideas of logic. It's very tempting to kind of interchange these two implications or get them mixed up in some way or inadvertently replace one with the other. But these are not interchangeable. A implies B is not the same as B implies A. What we need to prove, though, is that both of these implications hold. They don't always have to hold. So if we've got statement A implies statement B, it's not forced to be the case that statement B implies statement A. So for example, let's suppose we live in a world where all cats have 4 legs. So there's no cats that have been unfortunate enough to have an amputation or something like that. All cats have 4 legs. So if I've got an animal in front of me and it's a cat, I can assert, therefore, that this animal, because it's a cat, has 4 legs. Whereas it doesn't work the other way around. If I've got an animal in front of me and I know that it's got 4 legs, I cannot assert that it's going to be a cat. It might be a dog, it might be a lion, it might be a polar bear, who knows? But the point is, there are other animals, other types of animals that typically have 4 legs. Okay, but in some cases we can have bidirectional logic. So that's what we're hoping to see in this case, where the statement A implies statement B, and statement B implies statement A. So in symbols, we might write something like that. A implies B, and B implies A. So this symbol here is the logical conjunction of these two statements. Or more succinctly, we might write A implies and is implied by B. Okay? So that's just a little bit of symbolic logic. I used to like, particularly when I was doing A-level maths, I used to dip my toe in the water with symbolic logic. I didn't really get very far with it because I was interested in other things, but I found it really interesting. Okay, so when I started with this problem, I started with the idea that I was going to prove these implications separately, and that's often a very common kind of initial position to take, that if you need to prove an if and only if theorem, so a sufficient and necessary conditions, for example, it's very common to try to prove in one direction and then separately prove in the other direction. And that's the approach that I decided to take initially with this. So let's have a look at how that might work. So I started with the notion that our triangle is equilateral. So if ABC is an equilateral triangle, then my first idea, and this is a really good example of how sometimes you can you don't necessarily see the wood for the trees, and you make something much more complicated really than it needs to be. My first idea was to use the cosine rule. By the way, this is far too much more complicated really than it needs to be, using the cosine rule. I'm going to go through it. I'm going to go through the idea that I had, but even from the outset, I wasn't particularly satisfied with this approach, for the simple reason that I thought that the cosine rule was not, it wasn't elementary enough. I've got to use the cosine rule. I've got to rely on an additional property of equilateral triangles that I didn't really want to have to rely on. So an equilateral triangle, as far as we're concerned, is a triangle with 3 equal length sides. To use the cosine rule, I had to rely on the fact that not only are the sides equal in length, but also the angles, the interior angles, are all equal. This to me is, it's something over and above, it felt like something over and above what I should be doing. It works, but I didn't like it. So how does this work? Well, we get, for example, that a squared is equal to b squared plus c squared minus 2 bc cosine of each of these angles is going to be pi by 3 or 60 degrees if you prefer, cos pi by 3, which therefore we get a squared is equal to b squared plus c squared minus bc. And therefore, rearranging this, we get that b squared plus c squared minus a squared is equal to bc. Similarly, I can get that a squared plus b squared minus c squared is equal to ab. And finally, a squared plus c squared minus b squared is equal to ac or ca, whichever, it doesn't make any difference. And then if I add the left-hand sides of these three equations together and add the right-hand sides of these equations together, what I see is I get b squared plus b squared minus b squared, which is just going to be b squared, minus a squared plus a squared plus a squared, which is going to be a squared, and c squared minus c squared plus c squared is c squared, equals ab plus bc plus ac, or ca, which is exactly what I needed up there. But like I said, this solution didn't satisfy me. And this is kind of a characteristic of mathematical thinking, that just because you've arrived at a solution to something doesn't mean that the solution is necessarily, it doesn't necessarily satisfy you. Okay, it points towards the fact that that problem can be solved and you have found a solution to that problem, but mathematicians do like elegant solutions. Okay, so okay, that's I wanted to go for something that I felt was a bit more elegant. I wasn't happy with this solution, so it works, it's fine in that respect, but let's see what else we can get up to. And it turns out that there's something much simpler that I can do. Okay, so if this triangle is equilateral, then clearly A is equal to B is equal to C. Okay, that's what it means for a triangle to be an equilateral triangle. And by the way, it's really important when you come to solve problems that you first and foremost do understand the information that you've been given as part of the statement of the problem. So if you're told that the triangle is an equilateral triangle, you need to be able to pick out certain properties of equilateral triangles. First and foremost, you need to know what is meant by an equilateral triangle. So an equilateral triangle, as far as we're concerned, is a triangle with three equal length sides. Okay, and this is important in all other contexts. So, for example, if in another problem it might start talking about a circle. Okay, everybody knows what a circle looks like, but can you give a precise formulation or a fairly precise definition of what it means for something in mathematics to be a circle? I often ask my students this question during lessons. Can you tell me what a circle is? And I'll get all sorts of answers like, oh, it's a circular shape, or it's a round thing. And these are, in many ways, in the context of everyday speech, these might pass as definitions, I guess, or explanations of what a circle is. But in mathematics, they're kind of useless. To describe a circle as a round thing or a two-dimensional circular shape is kind of vapid, just vacuous, really. There's no content to these definitions, no useful content. So you might describe a circle. I'm not saying that this is the only way, but you might describe a circle as being the locus or the set of points which lie a certain distance from a fixed point called the center. And the distance is called the radius, for example. And that at least starts to give you some properties, some things that you can actually start to incorporate into your solutions. Whereas if your notion of a circle is a round thing, it's going to be very difficult for you to use that kind of definition when it comes to solving problems. So an equilateral triangle is one with three equal sides, and therefore A is equal to B is equal to C. Okay, good stuff. So that means then that if I interpret A squared as A times A, then this is also going to be equal to A times B. If I interpret B squared as B times B, I can also interpret this as B times C, because B is equal to C. And C squared is equal to C times C, which is equal to C times A. So now I just add the left-hand sides together and the right-hand sides. And what do I get? a squared plus b squared plus c squared is equal to a times b plus b times c plus c times a. That to me is a much neater solution to the problem, at least in that direction. We've got the implication in that direction, from equilateral triangle to this equality. Okay, so now we need to think about the other direction. If we start with this, how can we prove that the triangle is effectively equilateral? In other words, A, B, and C must also all be equal, numerically equal. And it's at this point that I realized that whereas, as I was saying initially, you might be tempted to prove the implications separately, and this is a perfectly valid thing to do. Sometimes when you've got an if and only if kind of theorem, where the logic is it works in both directions, sometimes if you're really lucky, but not always, you can prove both directions in one go. And that's what I realized when I went for the other direction, that what I was going to do, what I was planning on doing, actually worked in both directions. It actually covered both directions at the same time. This is the dream when this happens, but it's not always immediately obvious when this happens, or when this is the case. Okay, so let's start with a squared plus b squared plus c squared equals ab plus bc plus ca. By the way, if you haven't pressed that subscribe button yet, I'd be really grateful if you would if you'd subscribe to this channel. Okay, well, because this is an equality, I can just double each side. I can multiply through by 2. So I get 2a squared plus 2b squared plus 2c squared is equal to twice ab plus twice bc plus twice ca. Okay, so now 2a squared means a squared plus a squared. 2b squared means b squared plus b squared. 2c squared means c squared plus c squared. So what I can do now is I can write this. I can write a squared plus b squared plus b squared plus c squared plus c squared plus a squared. And this is equivalent to this. And this is equal to twice ab plus twice bc plus twice ca. And by the way, each of these is an if and only if. Okay, the logic is works in both directions. So if this is the case, then this is the case. If this is the case, then this is the case. And it's important that I get this at each stage here. So, subtracting each of these terms from both sides, what do I get? I get a squared minus 2ab plus b squared plus b squared minus 2bc plus c squared plus c squared minus 2ca plus a squared is equal to 0. Again, if and only if. So this factorizes now to a minus b squared. This factorizes to b minus c squared. This factorizes to c minus a squared. It must be equal to 0. Again, if and only if. Right, so now let's have a think about if I've got something like x squared. X squared is, assuming that x is real valued, we're not dealing with complex values here, is real valued, then x squared is going to be greater than or equal to 0. If x squared is equal to 0, this is true if and only if x is equal to 0. In other words, there's the only value when squared is equal to 0 is 0 itself. Okay, so since each of these, the sum of these three squares, a minus b squared plus b minus c squared plus c minus a squared is equal to 0, the only way that this can happen is if each of these is separately equal to 0. Because if any of these, if one of these, or two of these, or all three were positive, non-zero, there's no way that it's going to cancel out with any other, there's no negative terms. So if this turned out to be 2, for example, there's no way that that's going to reduce. Even if these were equal to 0, we'd still get 2. So for the sum of these 3 squares to be equal to 0, each individual square must be equal to 0 itself. Okay, so what does that mean? That means that a minus b must be equal to 0, b minus c must be equal to 0, and c minus a must be equal to 0. If and only if. But a minus b is equal to 0 if and only if a is equal to b. B minus c is equal to 0 if and only if b is equal to c. And c minus a is equal to 0 if and only if c is equal to a. So, starting with this equality, going through this sequence of steps, I show that a is equal to b is equal to c. And if I were to start with this, I could, in theory, just simply reverse these steps and get to this equality. Now this works, so this proves both directions simultaneously, and this works only because each of these is bidirectional logic. If at any stage the implication just became single directional, so let's say that, for example, for sake of argument, that this implication was just in one direction, then this argument wouldn't prove both directions simultaneously. It would only prove in one particular direction, from here to here, but not vice versa, not conversely. Fortunately, though, that's not the case. We've got bidirectional logic at each stage, and therefore the whole argument is kind of reversible. You can traverse the logic in either direction, starting here, finishing here, or starting here and finishing here. And that's the solution to this particular problem.